Hello, party people. 1, 2, Polizei and Skinny Seahorse. It's kind of disturbing that none of you ever talk in the chat. Hello, Igor. So, yesterday after the stream, I added a bunch of additional stuff. As you can see, I decided on a string concatenation operator, and it's ... because the addition operator is really just the thing that should be reserved for integers or numbers in general. I also managed to build out some of the grammar so that eventually we can write stuff like this. I haven't implemented it yet because I also need a way to construct records. The same is true for stuff like this. So lists will also need to be done before this can be wired up and emitted to the virtual machine. And the biggest thing I managed to do last night was, so yesterday we worked on external functions. What are external functions? We want to be able to call JavaScript functions from within our source language. There are two types of external functions. One type is synchronous or blocking. Think of, say, alert. That is a blocking thing, even in JavaScript. So as long as this dialog box is open, nothing in the UI thread of the browser is gonna get executed. So this is very easy to integrate with Paperbots program. It's just a blocking call, and the virtual machine doesn't need to give control back to the UI thread. The more interesting case is when we want a non-blocking call. That is, the Paperbots language itself doesn't provide a way to have things like callbacks that get triggered outside of the thread that it's running in. In JavaScript, you have stuff like, for example, set timeout. And what I did here for the external functions is, if we look at, I added a bunch of simple functions like char add, which just call out into the JavaScript equivalents because the base types of Paperbots in the virtual machine map to JavaScript types. So it's very easy to expose JavaScript functions like the string char add function to Paperbots. So yeah, this gives me L, which is at index 2. Again, this is a non-blocking this is a blocking function, so we can just wait for the return of this function in the virtual machine. What's more interesting, as I said, is non-blocking functions. That is, functions that will be executed in the future and will return a value. Now, Paperbots, as I said, is a single-threaded thing, just like JavaScript. But in JavaScript, you usually set up a bunch of globals, set up a bunch of callbacks, and then return control to the browser. And when you say click on a button, then your callbacks are going to get called. In Paperbots, we currently do not have a callback mechanism. By working design by Malang, moved it to static types yesterday. Cool. That's awesome. If you have a GitHub repository, just link to it. I'm happy to promote it. So anyways, non-blocking functions. Set timeout would be one of these. Another one would be request animation frame. So now the way this works is I added a new virtual machine instruction. Look at my shit. It's not ready either. I added a new virtual machine instruction that is called, where are we? It's called call external instruction. And when we look at the registration of that, I now have an external functions class where you can, this is essentially a way for you to build up a standard library. So to this I add functions. I give them a name, I give them the argument names and types, and I give them a return type, and then I say if it's asynchronous, that is non-blocking or blocking or synchronous. And finally, I give them a JavaScript function, or in this case a TypeScript function. Your shit runs basic code at least. Mine gets stuck with functions. Yeah, that's how it is. So the magic part is this. This is the JavaScript TypeScript that gets invoked when the virtual machine calls this external function, and it will pass the arguments that have been provided here to that JavaScript function. If we look at the machine code for this, let's just make it a little simpler. So you can see the call external here, and it gets a function index, which is index 9. Since this is an external function, the function will be looked up inside this external functions management class instance, which just has an array of all these functions that we added. So I don't know what index 9 is. It should be, yeah, this, I guess. So this is fancy. And this is for blocking functions. So the virtual machine will now totally wait until this function has returned. So let's look at how that works by debugging into it. There's the compiler, and we want to debug this call ext instruction. So I step and push stuff on the stack, and now the call ext instruction will be executed by the virtual machine. So we break into it. Let me just resize this. Okay. So what it does is, in this external functions thing where we put in all the external functions, it just looks up the function that we want to call by its index. The index is part of the instruction, as you can see. So it fetches that function, and in there we have a bunch of stuff. We have the argument types, which consist of a name. Okay, this is not what I wanted. This is what I wanted. This is what I, as a user or the creator of an external function, provide a name for that parameter of the external function and its type. And during type checking, we actually look up these types that I specified and assign the real deal, the real type representation to this array. And then we have the async flag, which tells me what to do with this, whether I should wait for it now or whether I should stop doing any interpretation until I get a result from that in the future. So anyways, this is a synchronous call. So it's gonna fetch the things, it pops the arguments from the stack, and now it calls my JavaScript function with hello and to, which we can step into. So yeah, here's where I defined my external function, and then it just calls the char add on the string value with this index. Pretty simple stuff. And since the function is not asynchronous, I can immediately check if there's a return type, and if so, push the result onto the stack for consumption by the rest of the program. In this case, we expect a string. Wait, what? Why is the return type a number? This seems incorrect to me. What function was selected? Since this is JavaScript, nothing breaks at runtime. So this is wrong. This should be a string. There's probably a bunch of stuff wrong here. ToString, wait, yeah, doesn't matter. Okay, so we push the result because we can immediately continue executing our function. Everything is fine. Now there's also another function which is called wait that waits for 400 milliseconds. That is, it blocks this program for 400 milliseconds. And the way this is implemented is as an asynchronous function. And this is where the fun begins. So again, I specify my wait function with a name, and it gets a parameter called milliseconds that is a number, and it returns a number, and the number is just for debugging purposes for me. It's essentially the number that was specified as the argument. Then we say that the function is asynchronous. That means the virtual machine will give back control when this is executed to the main thread and every time it's being called again to continue executing, it would say, nope, I'm waiting on a result from an asynchronous external function, gives back control immediately again. And the asynchronous function must return an async promise, which is a class or an interface inside of my compiler thingy. And that just tells me whether the function has completed and the return type, if any. So let's see what it does when we execute this. So again, we push the argument and then we call the external function. Here in the virtual machine, we look up the external function again. We pop all the arguments from the stack and then call the function. And the function, as you might have seen, is a call to set timeout. And set timeout is a JavaScript function that, given a bunch of milliseconds, will execute whatever function I provide as the first argument in so many milliseconds. And when that function gets called, then the promise is set to completed, and we also set the value, which is just the milliseconds. But the virtual machine gets the promise, it doesn't get the value. So let's see how that looks in the code. Okay, so I'm applying this function now. The set timeout is being called, and if 4 seconds pass, then we are done. So this function is asynchronous, so I store these in my virtual machine. And I also store the promise, and I'm done. Now, since I'm waiting for a promise, I should not execute any more virtual machine statements. Okay. It reloaded the page, that's why it didn't execute. I don't know, this reloading light server thing doesn't work half the time. Waiting done. So let's start this again. Okay, we push, we call. In here we fetch the external function, we push or pop the things and then call the function. And now we know it's an asynchronous function because that's how we defined it. So we set the virtual machine's async func and async promise to the function and the promise that was returned by this function. And then the next time the virtual machine is invoked, oh my god, it reloaded the freaking thing again. This is terrible. So the virtual machine is now continuously being called here. It should be though. No, wait, sorry. I need to step. So every time I try to run the virtual machine now that it's waiting for this call, it will check if it has a promise. It does. And then it checks if the promise is completed. It is. And if that's the case, it checks if there was a return type and pushes that on the stack. And we are done. We can now continue with our program. And this is freaking fantastic because that means I can even have something like, I don't know, I can do line. Let's just say I can do this, doesn't matter. Okay, so I can do this and this and this. And usually this would go, for example, to an HTML5 canvas, and then I need the canvas to update, which is done in a request animation frame callback, which is asynchronous. But I can write a linear or synchronous program to do that. I can just say I have a method present, which could then be waiting for request animation frame to have happened. And then I know this thing is actually now visible on screen. I don't need any callbacks in my Paperbots thing. I can just write a synchronous linear program, which is pretty freaking fantastic. This can also be extended to, say, key press events or mouse events and so on and so forth. So yeah, it's pretty nice. Okay, so as I said, I also added string concatenation. Hello. So there's a new new instruction for the virtual machine, which I call string concat, doesn't matter. I just push the strings onto the stack and then I call that, and that concatenates them and pushes the result back on the stack. Not very exciting. And I built up a tiny little standard library that lets me convert between booleans and strings and numbers and strings and stuff like that. So nothing too amazing. Plus, an alert thing that calls the JavaScript alert. Yeah, let's not do that. And also I think I called it print, that actually logs to the JavaScript console. Yeah, there we go. So yeah, everything is in shape for me to wire it up with the actual playground the kids see. So these functions are asynchronous functions later on. So I can write a synchronous program here, and the virtual machine will pause when it calls one of these until they have returned in the future, which is very nice because they do animation. So the virtual machine cannot block and wait until they are done. The virtual machine just needs to give back the control to the UI thread of the browser. So amazing. What I'm trying to build today, you saw the ghetto low-level debugger here with the stack visualization and my call frag. No one listens to Twitter polls. Nope. I just wanted to see what the majority says and do the exact opposite. Hey, Nominal TV. So this low-level debugger I'm gonna keep. I need to compartmentalize it, and then I want to write a high-level debugger. And for the high-level debugger, we want to have the standard operations of step through statements, not necessarily lines, because I can also write something like this. Then print hello. And stepping over this entire line would not work so good. So we actually need to emit information into our virtual machine code that tells us where the statement boundaries are between statements. So for example, if I make this a 10 plus 7 times 10 is bigger than 30, so I have a really complicated thing here. Okay, I must have fucked something up. This is not good. Why would you expect something? Oh, it's not 10, it's 2. Yeah, I'm stupid. Anyways, if I compile this to the machine code, and yes, the syntax error detection is terrible, but I can do nothing about that because I'm using a parser generator. Maybe next week I'm gonna rewrite the parser manually. If I look at that source code here, so the push 10, the push 3, the multiplication, the push 30, and the addition, and then the comparison, all of this equals this. I should say expected to... Yes, that was my point. I cannot fix that because I use a parser generator and it does all the error handling, and I have no way of modifying the parser generator's error handling. So that's why the error messages are crap at the moment. It's fine. I can only do so much in the allotted time of a week. So anyways, this whole thing actually corresponds to... Right? It is actually super simple. I wrote a recursive descent parser on a grammar that's very similar to this in about 400 lines of Java code. So it is actually super simple. And that beast can do proper error recovery. So I'm gonna essentially do the same for Paperbots. The hard part, or the tedious part, is actually the tokenization part and making it work with all kinds of special cases and shit. The parser itself is simple. You can look up basis minus template on GitHub. Then you see my super cool templating engine with a general purpose language. So anyways, what I want is this thing should be... Is it? I don't think so. It is really simple. I guarantee it. This is the whole parser. Oh, okay. Well, in this case it is, because this is for a templating engine, so I need to differentiate between text blocks and code blocks, and it's a little pain in the butt. But this parser is super short, 450 lines for a language that's much more expressive than Paperbots, because it can do stuff like, let's see. So this is how a template looks, and anything inside two curlies is being executed. As you can see, I can do field access. I can have all kinds of literals, as you can see. I can also have object notation a la JavaScript, JSON. Yeah, that's cool. That's why I said parsers are easy, even with proper nice error reporting and recovery. I just don't have the time to write one. It was so much faster to just push out the pack.js grammar and call it a day. Anyways, what I want to do is, when I step source level wise, I want to step over the header of the loop, over each statement, and I'm not sure if I want to step over the end here. I will probably jump back to the while. Yeah, I guess I'm going to do that. So what I need to do is, for all of the instructions that make up a steppable thing inside the source language, like the header, which might share the same source line, for each of these I need to write out a sort of index that lets me then differentiate in here when to stop stepping. So if I started here and said source level debugger, please step, then it should step until the print statement. So until here, and then stop again. And when I step again, it should execute the print statement and then stop here again. So for these lines, making up one of the parts, or making up a statement or a loop header, they need to be grouped into instructions that can be stepped over in one go, source level language. And then I also need to map them to the source line, so I can highlight the line I'm currently in the debugger in the source code. So what we're gonna do is we're gonna extend our function code thing, which holds the machine code for a function. We're gonna extend that function code thing. So we have the instructions, and then we have debug info. Let's call it line info. And that's an array of line info. And that should be what should it contain? Okay, it has an index. And then it needs to map to the source line. So the index would be, all of these instructions would have the same index. These, because they are the loop header from here to here. They would have the same index. Their line number would also be the same, 0. But then we have the second part, which is this statement inside the while loop, which also has the line number 1, but it has a different index because it's a separate statement in the source language. So these would have the index 1 and line 1. This would have the index 0 and line 1. So they share the same line, but they are separate when we step. Okay. I could make this easier and just do line stepping, but then if you have like something like this, it would get really nasty. So let's do it the proper way. Okay, so when I generate the machine code for a part of a statement, like this while loop header, I need to assign the information to the function code. Yeah, okay. Good. And then I can add a new source level step to the virtual machine that will just do that. That is, do a source level step based on going through all the instructions with the same index until I hit an instruction that has a different index, or until I hit the function call, or until I hit the return, because those are synchronization points for stepping over lines and statements and into functions. Okay. Yeah, this probably needs to be modified later on, so we make it a little bit easier to do. Okay. So the first thing we're gonna do, we're gonna emit this index / line information for each of the AST nodes. And here we go. There's also a second, There's also a second piece of information we need. If you remember, a function can have slots that represent the variables in a function. So I can have a foo, a number, and since this language has lexical scoping, I can also have an a here. Wait, I can't have an a here, but I can have a b here, but it's only valid in between this if. So when I debug and I display variables, I should only display variables that are currently in scope. So for each variable, I need to keep track of its liveliness of the line numbers within which it is active. And that's going to be fun. But those two pieces of information I need. So an index and a line info for each statement that I want to step over, and the line info for the start and end line within which the variable is within scope and should thus be displayed in the debugger. Okay, so we said we're gonna emit stuff. We need to emit the line info, emit program, emit function. And we can start here, because what this emit statement list does, it is used every time I emit a block of a compound of a control flow statement. So for this, I would emit a block. I just wonder. Yeah, I figured it wouldn't be that easy. Okay. Let's see. Okay, let's start with the simple case. No function, just a main function. Then var I 0 times 10 is its own statement. Var b equals. And then we have, let's say, a call to alert. And we want to emit line info for all of these statements. And for my final trick, I'm gonna do this so we can verify that stuff is correct. Okay. So the actual code emitter for an AST node is here. The problem is that at this point I do not know if this is a statement or if it is part of a compound statement or an expression. So maybe it makes sense to emit function, blah blah blah. So maybe it makes sense to tell the emit AST node whether the current thing I'm emitting is a statement or not, because I know that it's a statement in here. And otherwise, when I do the emission for an AST node like this, then it's not a statement on its own because it's part of a bigger statement. So I think this is the way to go. Then I can have all the line info generation in here. But it's gonna mess up my funky okay. Yeah, now I need to think about what I'm doing actually. Okie dokie. So if it is a number, boolean or string, we just push that. And I am not gonna do a thing here because I wanna, God damn it. Yeah. Let's build this up from the ground. So if my statement is just a literal, okay. Note context is statement. Yeah, I think we're gonna do this. This is probably a little healthier. Is it? This is terrible. Yeah. I am not sure if this is a good idea. Yeah, let's try it. Let's see how far we go. So this is a function init line info. It takes a node, which is an AST node, context, which is the emitter context, and whether it's a statement. So if it's not a statement, we can bail, because then somebody else is going to take care of giving this line information. And otherwise we have to switch on the nodes kind again. Default case is insert never for that node. And I can start string. I could probably just copy all of this and then get rid of the actual code. But it should match pretty well. Okay. So we now know that whatever node I have in hand is its own statement. That doesn't mean it's on its own line, it just means it was parsed as its own statement, as part of a block, say. So if it's a literal, then we know that we have emitted one machine code, the push machine code, so I just need to emit one line info for that. Let's see. Yeah. Okay. So the emitter context needs to keep track of. This is very cumbersome. Huh. Interesting. So the emitter context needs line info index equals 0. Okay. And that is going to be recursively manipulated by this function down here. So I know the next free line index of the line info, and I have the actual line information in the AST node. line the location. So that shouldn't be too hard. Context dot fun equal context dot fun. Yep, that is where we get our, and let the line info be the fun.line info thing. That we should rename to line infos. Because we have one info per instruction. Okay. Then let's fix this up real quick. False, false. This on its own. Oh wait, what the fuck? Yeah, okay, this is not. These two are definitely not their own statement because they're part of a binary operation. The unary operation. This thing is not part of it. Yeah, okay, so all arguments to an AST node are not the thing. But then I need to do this string concat. Yeah. I actually wonder if you break here. Yeah, I think I can do all of this down there. So none of these will be line infos. Yeah, so for function calls we won't step over individual argument evaluations. It's just one thing. The if statement. That is cool. This is gonna be hard. So there we emit the statement. So each of these blah 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 blah. Okay, for the condition, this is not its own statement. Where is it? Well, this is the loop header, but we're gonna deal with this in a different way. The repeat statement has a loop header which needs to be evaluated. Blah 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 blah. The return statement for the return thing returned. The break statement doesn't evaluate anything. The continue statement doesn't evaluate anything. The record and function don't do stuff. Comment doesn't get anything emitted, and these aren't implemented yet. Okay, so cool. Then I can actually, once I break out of this, I can call this on the node in one place, which is very nice. So inside the mid line info, I now need to know what my individual asts emit to, at least for the block statements, because those are the motherfuckers. But let's not deal with that just yet. Let's do it for the easy ones first. So I'm gonna kill all of this and do nothing. Push all the arguments. Yeah. Oh man, this is a little bit of a mindfuck actually. So we'll see if I can actually pull this off tonight. I have no big hope that I can actually do this and then the graphical debugger part as well, so we'll see. As I said, I'm gonna time box this to an hour, but I guess I just keep the stream on and babble. It doesn't make a lot of difference really. Okay, so we're gonna start with dealing with this. We know if there is just a literal that is a statement. let's put this down here. Okay, if we have a literal that was a statement inside a block, then we emit a line info for that thing. Okay, and at the end of it I need to text dot line info index plus plus. Okay, so this will help me count up to the next statement boundary, so to speak. So me push. I'm going to go for now. Good luck with the debugger. Thanks. Have fun. So I'm going to create a line info, and that has a line. Okay. An index. That's that line index we're talking about. And then it has a source file line number. And that we can thankfully get from the nodes. And we just take the starting line. Okay, so we have this. Now let's reload and see what the debugger says. We're gonna wire this thing up so it tells us the index and the source line. I guess at the end of it. Yeah, let's do that. So Paperbots debugger. There was a render method. Yep. So this is for the slots. This is for the thing. Okay. I should probably make this literal, but I'm too lazy. So how do we best represent this? Well, we're just gonna take the frame.code.instruct line infos index. So we first want the index, and then we're gonna print the source line. What are you doing? I'm building a programming language, and today I'm building a high-level debugger. At the moment we only have a low-level debugger. And that crapped itself because I didn't, what didn't I do? Undefined. Good. Debug. Let's see what we got in our little virtual machine. The line infos only has one instruction. That would make sense, yes. So it has a push and a pop and return. Okay. So these are things that are inserted automatically by a piece of code that makes sure that every function has a return statement at the end of it, and that if there's a statement that leaves a value on the stack, that statement gets popped. So for these we need to generate line numbers as well, or line infos. So let's see. This is here. So, okay, since I'm pushing a thing here, I also need to push a thing into line info, and the line info will just be the line info of the previous instruction, which should be fine because there must be a previous instruction in this case. Do we have an index here? Okay. system context dot instructions event -1. Well, there we go. So that's one part of the equation, and then I just push that previous line info for this artificial pop into the line infos as well. And for the function call, I need to do the exact same. So I think I can just copy that floppy. Like that. Let declarations of the is that a block? What? Oh, yeah, it's not a block. God damn it. There is a semicolon missing on line 752. Yeah. There are multiple semicolons missing now because I copy and pasted like the not good citizen I am. Okay, we should now get a thing for the pop as well. So let's see what the compiler does. Debug. Okay. Yep, that seems correct. And then I also have the return instruction, which I generate in a different place. Let's see, that should be for the function call AST nodes. Oh no, god damn it. Alright, I'm just gonna copy this again because this is gonna work again. And then I need to see where I emit. Oh yeah, here we go. This is the magic part. And this is where compilers become really, really fucked up, because you tend to have to start adding places like this where you need to emit some kind of information that's distributed across a bunch of functions. So yeah, that's not fun. And now we should have all the info we need. Okay, so this is correct because all these three instructions belong to this one tiny little thing. Okay, moving on. A binary operator. If that is a statement, then I know the binary operator consists of three instructions. Is that correct? Let's see. Oh, that can have children. That is nasty. Ooh. Yeah, it might be that this strategy doesn't work so well. Yeah, I have a feeling this doesn't work so well, so I need to plunge all this information into my code emitter, which sucks. Okay, still way around it. I would have to record the start instruction and end instruction of each AST node that I emitted before I called this function. And that's not gonna happen, because then I end up writing even more code in here that's just bookkeeping instead of let's see. we're gonna kill all this because fuck the world. And then we can keep this. Yeah, we can kill all of this. We might introduce a new helper function later on to make some of it a little easier, but what do I need to do? I need to do this here. So let's just get this. So I need to remember when I emit an AST node, I need to know where in the virtual machine code instructions array the emission started. So the start index of that. So I know how many line infos I need to emit for an AST node with multiple instructions, like the repeat and so on and so forth. So last ints index equals the code.length, and we're gonna rename this code.length because it is a terrible thing to call it, because it's the instructions of the function. Okay, so now I have this is the start. Then I know for how many instructions I need to emit the line info. Okay, and the line info I can increment at the end of the emission, so let's do that here. The context.line info index is one bigger, and then we have a function with line info. So we have the line info index, we have the source line, and then we have the num instructions, for how many instructions I need to emit this. And I need the line infos, which is an array of. Okay, I'm just building a tiny little helper function here, so I don't need to write all this crap in every case statement up there. So this is bad, kids, don't do this at home. I'm a professional, I know what I'm doing. We're gonna share this thing because there's no point in. This is the line info index, and the line is the source line. Okay, and then we push that for as many instructions that the AST node actually that were emitted for the AST node. So line info, this looks good. Okay, I like this. Now I need to add this for each AST node. Okay. Get line info, and I only need to do this if this is a statement. So if this is a statement, then the source line is the node's location start line, and the number of instructions is the last in's index. So how many instructions, however many instructions I've pushed to this instructions length minus, and that should do the trick for our literals at least. Okay. Okay, so this worked. Let's try it for a binary operation. Yeah, this craps itself because we haven't done this yet. So, okay, I like this. This should work. Why is this index 2? Oh, this is index 2 because we should only do this if this was a statement. Then we know that we fucked around with line info indices. Yeah, that's good. So all of these are the same group of instructions. They belong to the same thing. And they also have the correct line number, which is 1. If we do this, then the line number still stays 1, which is fine for me. I'm not gonna care about the, hey, this thing can span multiple lines. At least not now. I can do that later if I wanted to. Bye, Yuku96. 96, are you born in 96? Oh my god, people are so young. I used to be young. So, does this work? You have now 2 statements. This and this. This seems to work. Let's put it on okay. Perfect, this is exactly what we want. So I think we can continue with this strategy. Let's see. So we finished the binary op. We can do pretty much the exact same for the unary op. For the variable access, we can do the same, but let's not get ahead of ourselves here. So there's an unary operator that would be like a minus. Oh, yeah, that sucks because it thinks that this is now all. That's if you don't have semicolons to denote your statements, but we can make it. Maybe we can make it so. Oh, we can't. Why? So what does the AST node say? Block has an unary operator and a value and a number. That looks good to me. Okay, we must have fucked up the emission here. Well, you gotta press Command S to save your shizzle. Yeah, that looks better. So let's keep the other test cases as well. So literal, binary. This is the literal. This is the binary. Is that correct? Push, push, binary pop. Yep, that's correct. This is the unary. It's also correct, and this return gets the line info from the unary op. Wait, is that correct? No, that's not fucking correct. God damn it. Why is this a statement? Ugh, yeah, don't do this. Stupid. Okay. So, this is one group. I'm gonna fix up my debugger. So it will actually put a new line there. Okay, last line info index is -1. If last line info index is not the line index, then we output, god damn you, then we output a new line so I can see the groupings easier down here. What the fuck? Yeah. Perfect. So this should be line 1. This should all be line 2. And this is all line 3. Okay, cool. Now we have an easier time figuring things out. Also, okay. So I think I'm gonna make these because I'm going to probably gonna change up the format for the line infos later on. I want them all to be emitted by a single function so I can fuck around with things. So that gets the context, find.line infos, the line info dot index, line info dot line, and one additional instruction. So now everything goes through this method, our function. Okay, so if we have a variable access, the problem with doing this is that I first need to actually fix this up. However, I know that this is always a statement. Should be, yeah, it shouldn't matter. Do this. Okay, and then this is also okay. So I can have a var, goddamn you, var a equals 0, and then a variable access as its own statement. Perfect. So line number 3, is that correct? Oh, line number 4 is that, yeah, that's correct. Line number 4 pushes a 0 and then stores this in variable 0, which is what we want. And then we have the line, the variable access, which is its own statement in line 5, and that gets the correct thing. And that is good. Yeah, the function call, same thing. Oh my god, this is actually easier than I thought it is. Although I have not come yet to the to the fuckers of all motherfuckers, which is these composite statements or compound statements, if, repeat, while. So let's just do the others first. The return is always its own statement. The break is always its own statement. Yes. Then the continue is always its own statement. So these are done. Down here we don't have to do anything. So what is left? Let's see if this also works in functions. Debug. Oh no, we fucked up. It's broken. Cannot read property of code. Who calls it code? Oh no. What? Cannot read property of index of undefined. Okay. We got a special thing here somewhere. The line info. There is no line info yet. If there's no return instruction at the end of this. Why is that null? It shouldn't be null. Okay. Let's make it real easy. Yeah. Stop fucking annoying me. Okay. So that line info is undefined because no line infos have been written for this function because there is no instructions in this function. How can that be? Is null or kind is not null. Ah. Okay. That makes sense, I guess. But how can there be no instructions in this function? Oh, that's the main function. Ah. Okie dokie. So we don't actually do this if instructions are okay, and this should only be the case here because here we know that we actually put a value on the stack, so there must be some instructions in the function there. Okay. Yes, yes, just do the thing. Okay, this worked, so let's see. We are still broken. Why are we broken? Index of undefined line infos. Well, let's see. There's a restruction, which is a return. And then there's line infos is 0. Go freaking freaky. Yeah, that made sense. And because I push the return here, okay. So there's two cases. In one case the function has no instructions, so insert a return, or the last instruction in that function is not a return and I add another return. I should probably make it so these are separate things. Okay. If there is no instructions in the function, that means the function is essentially empty. In that case, we don't have any line number necessarily, because the main program, well, actually we do. So, oh, god damn it. Yeah. Let's not split it up. Let's decide this internally. Okay. So in either case, I push a return. I can get up the last line info here. before I push that return. But only if instructions is greater than 0, otherwise I have a null here. Okay, so if there was a previous line info, then I have it now. If there was not, I do not. So if line info, then I can just push it. Line info is push line info. So otherwise I need to construct the line info. I need to construct the line info, and I'm gonna use my emitter thing again. So that's context.fun.lineinfo. The line info index. I know there wasn't any instructions in there, so this becomes null. And then this becomes the we have an ASTS and the location.start.line. And then the instructions is 1 in this case because I only added return. So goodie, this should do the trick. We are looking good. So the main function only has a return. It's cool. And then we yeah, that's not good. Well, okay, this should be fixed. We are back at emitting line number information for the remaining thingamajigs. So we had the literal, we had the binary operator, we had the unary operator, we had a variable, we had a variable access, we have an assignment. For the assignment, that's also a single statement. So I can do this. Okay. Line 6, line 5, line 4, line 3, line 2, line 1. Cool, this looks good. So the function call, we also need the function call. See if that works. Can't find foo. Yeah, that's because it's not called foo. So this is in line 11. The pushing of the arguments is here. Let's make this a little bit more complex. Just so we know stuff works. Yeah, okay, all of this is in line 6 now. That's good. If I make this an assignment, we should still be good. Yep, still good. Okay, so we managed to do the function call. I managed to do the assignment. All of these are done. Now comes the shitty part. While statement. Let's put it at the top so I see it immediately. Okay, so this should crap itself because we don't emit line numbers yet. Perfect. I mean, it's not perfect, but it's cool. So the condition index, what do we have here? Info. Okay. So I emit the condition here and then the rest of the header. So we want to emit a line info for all of this, for all the instructions here. So we're gonna do this. How are we gonna do this? Okay, this should just work as is. And now for my final trick, I need to increase this. So we create a new group of instructions, so to speak, that have the same line info. Okay, and jump past false. Why is this here? Patch in the address, emit the false block. Oh, we're in the if statement. Well, it's still okay. So we should change this into an if statement. If 1 and 2 together, then okay. So I'm emitting the line info for this thing here. Then all the blocks, all the statements in the block get emitted recursively, and that does the correct thing in terms of line infos, because we already know that these statements work. And then we jump to the else. No, we jump past the else, which is its own instruction for which, so for this instruction, I need to create a new line infos. And what kind of line infos is that? Well, it's essentially the line info of the last instruction that we emitted, and that last instruction is either the instruction of this statement, or if there's nothing in that true block, then it's this condition, which is fine because we want this jump to be part of whatever was last evaluated in this true block. And if there's nothing in the true block, the last thing we evaluated was the condition of the if statement. So here I need to take the last line info and push that out, and we already have the code somewhere for that. So we're gonna take this. Wait, this is stupid. I should just be able to duplicate the line infos. So line infos dot push line infos dot -1. That should do that trick. Okay, so we covered the conditional, which gets its own line info, then the else block and the jump past the false block, which all seems to work. Then do I need to okay, so I need to do this here as well, because now I'm done. Okay, this is good. Then I am blah blah, jump to false, blah blah. Where's the jump to false thing? Yeah, that's fine, I guess. Okay, let's see what the debugger gives us. So pushing the to operator, blah blah. Okay, the whole header is now the same line index. So if I step over this, and then I just step in here, and that's those two statements here in the true block. Or I jump to instruction 13, which should be here, yeah. And that is its own thing, and that is its own thing. Cool. So I think this is good. Let's see what happens if we don't have any statements in those blocks. Well, it didn't crash. That's already amazing. Oh, cool. All of these become a single block. So even if this is true, it will just go right next to the next statement, which is exactly what we want. Just playing around here. Yep, that looks good. Yeah, all of that looks good too. Cool, so we managed to do the if statement. Now we need to do the same for the remaining statements. What am I doing here? This is the while, so I emit the condition here, then I emit the statements. What? Patch of all the continuous channel. Okay, so I emit line info for all the statements up until here, which is the condition of the while and the jump, which is good, I guess. Okay, and then then I emit all the then I emit all the statements inside the while, which get their own thing. I patch up all the continuous. I don't have that in if. Okay, that's cool. I emit the jump to the loop header, and that should probably get the same. Yeah, this should get the same as the last instruction. So we're gonna do this trick here. Man, this is nasty code. Emit the jump to the loop header. Patching the things, patch up all the continues, and we're done with that. And while true, do. So push true and jump if it's false. This is the header. This is his own group. Okay, then I push this value and pop it again because nothing consumes it, and I jump back to the header, which was this thing here. So if I step in, yeah, that's what I would expect, I guess. Yep, because I checked the condition again. And then the rest of the bullshit is its own groups. Perfect. As you can see, it would have been way easier just to go by the lines, but this is a nicer way of doing it actually. So emit the count, which leaves a value on, now we're in the repeat, and I think that's the last one. Yes, oh my god, fucking finally I need a break after this. So we're gonna use this old trick to emit a line group or statement group for stepping purposes for jump if false, blah blah blah. All of these statements are their own thing. Yes, that's correct. All of these statements get the thing. We don't need to do anything here. This is the bottom. This is the bottom of the loop header, which decreases. So this should be pretty much the same as this, only we need to do it 3 times. This is nasty. So for each of these I omit the line info of the last instruction inside that repeat thing. So that gets merged with the loop down here. And then I also need to do this for... Do I need to do this for the pop? Yeah, I'm gonna do this for the pop as well. They all share the same thing. Okay. Let's see. How are we doing? Repeat 7 times. Do and debug. So this is the repeat header. That's all one thing. So if we step, we stop here, and if we step, we get to this big nasty ass statement that pops the thing. And this is our count decrease and jump back to the head. Line 6. Yeah, I'm not sure. I have a feeling. Yeah, the pop shouldn't be part of this group. The pop should be part of the header because it is sort of. So I need to remember the header line info. Where am I omitting this? Line info. Okay, I need to get the last line info out of here. Line info is this. And then I push that for the pop. Yeah, so the pop is now its own thing. This block will always jump to the header. The header will evaluate, and if it's false, it will jump to this. But if we do source level debugging, then all of these will be part of that one source level step that we want to do. So we will end up here when the repeat header has decided that it's time to stop repeating stuff. And we're done. I cannot believe it. Amazing. This is stupid code because fuck, sorry. It's stupid code because it's very easy to fuck it up and it's really hard to trace. I remember we did something like that for RoboVM, the Java bytecode to native code compiler that we worked on. Well, Nicholas actually wrote that, if I remember. And he had the additional fun problem that he wasn't working off of an AST, which makes things a little bit easier, but we had to reverse engineer line numbers and those blocks that should be stepped in one step from the bytecode, the JVM bytecode. And that isn't as nicely structured as this. Eclipse, for example, the Eclipse Java compiler will emit bytecode for loops that is real fucking crazy. And we had to spend a lot of time reverse engineering what the fuck is happening. Because the jumps that were emitted for the loops were just fucking crazy. Yeah, so what I'm doing now is I'm gonna take a break, about 10 minutes. And then I shall work on the graphical. Oh, actually, I can retrofit my low-level debugger and I will have a step source line thing here and highlight the line number I'm at in the debugger up here. That should be the goal, because then the rest should be really easy for tomorrow. Then I can stop early tonight. Okay. And we're back. So we're gonna refactor our virtual machine now. So at the moment we have this run num instructions thing, which is nice, but not exactly what we want. We want to have a function or a method that can take a single step. So let's factor that out. Step. And there's a lot missing now. That's not a big deal. Frames stack. Let's see what's missing. The functions. The external functions. This should be a private method. Nobody should ever touch this. Okay. Perfect. Let's see if this still works. Seems to work just fine. Okay. So why am I doing this? Because this thing here is used by this thing. I have an infinite loop somewhere. And it's also used by this step function. This just calls it with a 1 for number of instructions, so we get to do this fun bit here. Now what we want is another step function that actually runs until it hits an external function that does not return immediately, and also runs until it changes from a block like this to the next block. So let's have a function step statement which should do pretty much this, except that our condition here will be different. So if it's an asynchronous promise, blah 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 blah, remove all of this. So let's think about this. This should step, that is, execute one instruction until we change group or we returned. Okay, so we need to remember what the frame index is. That is the frame we are currently in. If this changes, that means we stepped into a function or stepped out of a function. We're only going to use it for stepping out of a function. For the asynchronous promise, we already do the right thing. What do we also need? We need the line info index. We need a better name for this later on. So let's see. Should put this somewhere else. Let's go put it here. So in this, down here we now know that we have at least one frame, so it's safe to access. Dot PC. So we get the last frame, the top of the stack of frames. And from that we get the PC. Frame index, and from that frame we get the PC frame dot code dot line infos PC dot index. Okay, this looks good. Okay, before we do this, I actually want the step function to highlight the active line up here, which we can already do because we know the line infos. So for that we need to get line number that returns me the current line that we are executing in the source level, or a -1 if there's no such thing. So these two statements are the guards. It's terrible having these guards in here, but what can you do? Let's make them a little smaller. Probably put that in a function, but yeah. So in this case we want to return, if we're complete, we want to return -1 because we are no longer having anything that we execute, so that's good. Otherwise we know that there's at least one frame on the stack, and we can get the line we are at like this line, and we can immediately return that to whoever called us. So good. Then we need to add a new button called step line, I guess. So we're gonna go into our test HTML. There we have this little thingy. Step line. The value is step line, and this is a step. Okay, and then in Paperbots debugger, this is where we do a lot of stupid shit. Let's see where we have the other step. I don't know what I called this. Step line. Yes, this is a lot of jQuery, so I hope you're in awe at the amazingness of this terrible code. So this should now enable and disable this when I click on debug. Stop, this is good. And then I just need to wire up what should happen. I click step line. What should happen is it should step the statement, then render the VM state, and we also want to change the highlighted. What? Why doesn't this work? Okay. is not good. Style active selected. Oh, but it works in the work here. Yeah, it works here. So I'm missing an include or something. Ah. I'm missing active line. I'm probably missing. Yep, that's exactly what I'm missing. Yeah, that's much better. Okay, so when I click on this, then this should immediately set the active line to the first statement that we're gonna execute. So let's try to make that happen. Let's create a little callback function line changed. That is a line and it gives us nothing. Okay. Ah, wrong thingamajig. I'm not gonna do this in the run. In the debug, when I click this, I compile, I render the VM state, and then I can call this. Have I pushed a frame in this case already? Yes, I've pushed a frame. So the get line number will work. Okay, very good. So I clicked on this, and then I have line changed beyond dot get line number. Cool. That's one thing. And we're also going to do it here and here. Okay. Now we need to wire this up. Okay, we're gonna assign this default thing that does nothing, just so it can never be nulled. How do we wire this up? This creates the code editor, this creates the thing. The code editor should probably give us a way to set the line number. So where's the code editor? Here's the code editor. So we're gonna add a public function that's set line number. Okay. And then this editor dot set active set line. Who the hell knows? Set line. Set the content of line. Nope. Set cursor. That's it. What does this take? Set the cursor you can as a single line object or the line and the character as two separate parameters. Why not a character? Okay. I'm just gonna assume this is 0 based. Well, guess this will do. Okay, so debug. That didn't do a thing because I haven't wired it up here yet. good. It's probably called set line number. Oop, set line. Debug. That didn't work. Show me the console drawer. Number. Tells me -1. Why? Let's see. Frames. What? God, this is so terrible. Oh, yeah. If you don't look at the red squiggly lines. Oh my god, this is bad. This is not good. Why is there a window of frames? This is so terrible. Oh. Okay, let's see if we can find the frames. Oh, frames. Okay, should be fine. Should have caught them all, like good old Pokemon. Okay, debug. Give me the line number. Well, that seems to work. So let's step into that and see what happens next. Okay, that should set the line on the editor, so we should end up having this selected. Line 5 is not what we want. Ah, so this set line apparently. Oh, that's funny. This set line must be this. Okay. Let's go. So, step. We're still at line 5. And now we go into, oh my god, it works. It's beautiful. So it now should jump back to the header. And then jump to the pop, but still leave the line where it is. Oh, fuck, no. Oh, 7 times, yeah. Let's not do it 7 times. Let's do it 1 time. Cancel. Debug. Step. Okay, it's now at the pop, which means that works. And then we step again. I am so happy right now. First try. There's a question. What are the benefits of linearizing the AST? I'm currently also writing parser interpreter for a very simple language. So there is no... well, so if you're trying to get a little bit more performant, then a linearization is nice, because this interpreter loop this interpreter loop here, no wait, yeah, that's it. This interpreter loop that fetches an instruction and then decodes it and executes it, you can make that really fast. And you don't have as many recursive function calls that you would have if you go into if you interpret an AST. So if you write this in C, you can make it actually pretty occasionally fast, like Lua levels fast. An AST interpreter, like Ruby used to have an AST interpreter, they are usually a lot slower because every time you want to execute one AST node, you actually have to recursively call something that can execute that node. So you're pushing and popping a lot more stuff onto the stack. That being said, you could probably write this interpreter in a linear fashion to some degree, but it's really complicated. So I would not recommend that. Like, you could have a single function with a stack and simulate the stack yourself. That is one part of the equation, like performance, and maybe later being able to write to a different kind of virtual machine or even machine code like CPU code. That's one thing, or LLVM IR actually. The second problem I had to manage was that this is JavaScript, this is a single threaded thing, and if I want to call functions, I've shown this before, so I can call JavaScript functions from my Paperbots script. The wait is set timeout. So here's the external function that I inject into the virtual machine as well as the compiler. It's called wait. It takes one parameter called milliseconds with the type number and it returns a number, which is the milliseconds that are passed in. And then it says it's an asynchronous function or a non-blocking function. That means this does something in the future and my script needs to wait until that something in the future is complete. This something in the future in this case is a call to set timeout that will invoke this function here once the timeout occurred. Now, if I busy wait for this function to return in JavaScript, I'm blocking the entire tab, and that's no good. So I need to give back control to the browser engine, to the UI thread, while this thing is going to happen in the future. And once this thing happened in the future, my virtual machine can start running again. And the way this is done is, as you saw, this external function returns a promise that says, am I completed or not? And the virtual machine checks, so the virtual machine, this is the outer loop that runs num instructions, that checks if there is an async promise we are waiting for in our script. Because if that's the case, here we can bail on the run, and that will give back control to the browser to do event handling and all of that other stuff that's going on. And this run is being executed in a request animation frame, which is a callback that we get from the browser every time we want to render the window anew or the tab anew. So what happens is request animation frame comes and says, hey, could you please render the next frame for me? And then I execute this virtual machine for a bunch of instructions. But if I'm waiting on a promise, I bail out immediately and the request animation frame is then complete and then the browser can do stuff again. With an AST interpreter, I would have to like, say you evaluate this kind of thing with your AST interpreter, right? You would recursively go down that AST and execute individual nodes inside of that. Now, say you are down here, you have a call stack for each, a call stack frame for each of these nodes now in your implementation of your virtual machine, your interpreter. And now you encounter an async method, an external one. How do you save this recursive call stack that you built up while walking your AST for interpretation? That is really hard. I mean, it's not impossible, and it's probably easier than I'm making it out to be, But I considered this long and hard and asked my friend Michael, and we both eventually agreed that it makes more sense to linearize it. And if you look into the implementation of the code emitter, the thing I'm currently scrolling through, that's the entire linearization. Just that. Okay? And that's not only the linearization, that also outputs all the debugging information that I'm using done here. So this is not a lot of code for linearizing an AST for a language that's semi-complex. So yeah, you get a lot of benefits from linearization performance. You can do this asynchronous waiting more easily because you don't have to save a recursive call stack of an AST interpreter, but you only need to save the frames in the language that you're executing, which is a lot easier, as well as the program counters for each frame. So this is the entire state I need when I execute the virtual machine, and I can pause this at any point in time, and it's very easy to resume that. Not so much in an AST interpreter. And also in the future, it gives me a very easy way to emit a different kind of bytecode or machine code or virtual machine code. I could just rip this out, or I could just take this and augment it a little bit to write out a typed virtual machine instruction linearization. And I could run it on WebAssembly, for example. Yeah, so lots of benefits, and it's not hard. I would say that this is easier if you need to pause your virtual machine than using an AST interpreter. Okay, let's see, what was I about to do? Step line. Oh yeah, that's not implemented yet. Oh, it crapped its pants. No, actually it's not crapping its pants, it's looping forever. Yep. Okay. Yeah, that's not good. Funnily enough, the Chrome DevTools are still not as well versed in stopping infinite loops. This is terrible. I think I need to close these down, and then I need to click on this, or just kill the tab. And I cannot kill the tab. Exit page. Thank you very much. Oh snap. Good. Debug. All of this is one line, so it stays like that. Perfect. Fun, foo, a, number, b, number, and I just want to see if this actually works. I'm mildly optimistic that it works. Okay, this is my call stack. I'm currently stepping in this line, so this is good. Ah! Oh my fucking god, it worked. It moved the line cursor up here. And it's done with that. Why is the result none? Well, you could use web workers for VM print, but I guess no, you actually can't. I looked into that because say I have a pause button here that should pause the running VM in the web worker. That doesn't work because the web worker cannot get events while it's busy looping. Yeah, you can actually look at the source code of this. It's at github.logic/paperbots. Here. Yeah, web workers, what the fuck, I agree. I would have done it that way. That was my first instinct. Just have this separate thread, right? And then through some shared mutable state magic, I can have essentially atomics with which I can communicate with the web worker that executes the virtual machine. Well, turns out you cannot do that. Now, my question is, why the hell is result a nan? It shouldn't be a nan. So let's see, I push a 2 and a 1 and then a call. And A is undefined and B is 1 and result is 2. That's not nice. So I must have fucked up the interpretation of the function call. So this needs to be done by Friday so I can have some kids work with it. It's gonna be so full of bugs, but I have a fallback plan. I have Tony, the Python IDE, and we're just gonna switch to that if this doesn't work. Let's see. So my call did a thing that it shouldn't have done. So let's step. It's really valuable that I wrote this low-level debugger right pretty early. So now we should enter here. Okay. What are the locals? Okay. So the function is just 3 locals, the 2 parameters and this result variable. What's the stack look like? The stack has 0 and 1 on it. And the new frame has 3 slots and those values are 0. Oh. Yeah, that is wrong. Pretty wrong actually. I shouldn't start writing the parameters to the last slot. I should start writing them to the index of the last parameter of that function. Well, good thing we have a debugger, but at least that's easy to fix, I think. So let's see. We have the locals. I'm just gonna write a thing into the function code. We have the locals and we have a num parameters, which is a number. And let's see where we go straight with this. Locals. Num parameters is fun params dot length. Good thing we have that information in the AST. And let's fix this down here. So it's num parameters -1 here. Args. This should be correct though. Yeah, we're gonna test this in a bit. Okay, this looks good. So calling into the function, we don't need this anymore. I'm pretty confident that works. So I load this and this. Is this correct? Let's see. A is 1 and B is 2. Yeah, that's correct. 3 store. Perfect. Okay, so the only thing we need to do to make it a little bit more pretty is that we don't call this if number is -1, because that indicates that the VM is no longer running. Okay. 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 Wow, I'm so happy this works. It's fantastic. Stop. Okay. Okay. Cool. So now the last thing I want to do tonight, and I think I'm gonna stop with that, is implement this step line, which will do all of this for me. So we need a step line, and we need a, so I want to step over and a step into. Let's see. This should be easy peasy. So step, what does step do? Does it increase the PC at the end? No, it does not. That's one problem with this. What does it? Oh, it increases the PC here. Yeah, we need to increase this before that. So that's correct. Yeah, we need this because of the jumps. Okay. Okay, so the step should stop if we can step while there is no asynchronous promise, or while this equals the frame index we had before, which is when we step inside the same function. Ooh, this is gonna be complicated. Let's make it more true. If this won't async promise, then return. Because we know we are now at the place where we have to wait for an external function to return to us in the future. Okay, then when can we also stop? Let's run this little thing again to have an example. So here we have saved that we have one frame, and that's the frame index. We have saved the, what else did we save? We saved the line info index, that's the 0 here. And we essentially want to step until this changes. So we need to get that line info index out here. That's the current frame. That's the current line info index. Although we have to check if this dot frames dot length is 0, we can also return. So we know we still have a frame. We now fetch the current frame, and we know that this line info is also correct. So we can also bail if the line info index is not the current line info index anymore. Then we return, and we also, wait, frame index is current frame index is this and this and this. Use current frame index here. This is not going to be the fastest stepping thing in the world, but it's hopefully going to work. So we bail if there's an asynchronous promise. It makes sense. We bail if there are no more frames on the stack. We bail if the line info index changed, which would happen So those are two statements, they have different line infos. So this would bail if we hit this. What happens when I step into a function? When I step into a function, then the frame changed. Okay. Yeah, that looks good to me. So let's see if this works. How did I save this? Okay. Yeah, that didn't work. Does it? Nope, didn't crash. And that's also not what I want. Are we still executing anything? No, we're not. It's a little weird. Oh. Oh, okay. Yeah, I have to... do this at the end. It doesn't matter, it's not pretty, but I do have to do the same here. Probably. Debug. It's fine. Okay, so step line. Step line. Where the hell did we go? Stop. Step line. Step line. Okay, so one. Okay, this should now be the call, and that should change the frame index. Yes, the frame index is now different. But the line info index it's interesting. Okay. So if this changed, then we're gonna bail if the frame index changed. We're gonna bail. I remember implementing this for row VM in the debugger. It's stepping is really hard. Okay. It should be a lot easier with this though. Yes, this looks much better. This doesn't look so good. Okay, let's see. This should jump back out. Let's see. Step, 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 step. Okay. Okay, it should go back out of the function and return to line 7 for the final return. So let's see why that doesn't happen. Step, step, step. And steppity step. Okay. The current frame, the frame index should be 1 and the current frame index should be... The reason you don't use the VS Code debugger? I've never bothered figuring out how I can debug the browser stuff in the Visual Studio Code debugger. This works for me. Also I get to use this and a bunch of other stuff. I might not only be interested in just debugging this, I might also want to fuck around with the CSS and so on and so forth, so no real good reason, I guess. Okay. The current frame index is still 1, which is okay. The current line index is 1 as well, which is okay, so we don't bail. So this step should execute the load. It's the PC here. PC is 5. Okay, this is the return. And now we should have popped a frame from the stack. Yes. Oh, it crapped itself here. Okay. Why is this swallowed? Why don't I see this? So, yeah. If you copy paste the code, you're gonna have a shitty time. Yeah, we don't need this anymore. This should work now. Step line, and step line, and step line. Holy shit, it works. Now this is a step into function, so let's call it that. It would be nice to also have a step over function, don't you agree? So let's rename this to step into. And we are calling this, what do we call this? We call this here. And I'm going to rename this to step into. That's probably a better way of doing this, but all the features. Yes, all the features. So this is step into, and then we're going to have a step over. Anything else we need here? No. Okay, so step over, we need to add this down here. So whatever we did for step into, we do for step over here. Okay. So for our final trick for today, let's try to figure out the... Yeah, Alexa run code would be nice. So step over. So all of this can stay the same. We are also trying to replicate jumping from one group of instructions. Let's add another one down here. Print. So we want to keep jumping between these blocks, but we don't want to stop when we encounter a call or a call X'd. Let's do this as a test. We don't want to stop when we call X'd. Okay. Okay, I think this should actually be it. If the current frame index, oh, that's not good. If the current frame index is the same as the frame index we were in when we did a step over. Wait, is that true? It's not the same. The current frame index is either the same. Then we check if we jump between one of these blocks with this, or if it's, yeah. And the other condition is if the current frame index is less than the frame index that we had when we, because then we jumped out of the function, and that's also a step over. Let's see, step over does nothing, because fuck the world. It's not getting called, so maybe we should just make it so, yeah, this shouldn't be. I'm building a programming language for beginners that's executed in the browser. I managed to write the parser and type checker and virtual machine and emitting code for that virtual machine. I have a debugger, a low-level one, and I'm currently working on the high-level one that lets you step over statements and into functions and display local variables. So, step over. Oh my fucking god, it works. This is so much fun. So step over, step into, step over, step over, step over, step into. Doesn't work on external functions. Step over, and we're done. Okay, now the only thing that I want to know is what happens if I do this over an asynchronous external function. Step over, step over, step over, step over, step over, step over. Yeah, it does exactly. Yeah! Oh my fucking god, it works. I am so freaking happy. I have a full-blown fucking debugger. Step over, step into. You can see the 1 and 2 that I passed are correctly denoted here. I still need to track the lifetime or the scope of those variables for debugging purposes, so I only display the variables that are currently in scope and the life. But that is an easy trick. This was way harder. I can't believe it. I got step over and step into working. First try. This is super cool. Oh my god. Okay guys, let's write a Fibonacci thingamajig and do this recursively. Let's see if we find a Python version of that. This looks good. Let's just copy and paste that and rewrite it in Paperbots. Okay, so we have a function called fib, and it returns a number and it takes a number. If this, then return n, else we do this and this. because this is also fun, because we can now check that the step into of those function calls. Next minifig code snippets including fib. Yeah, one thing after the other. So what's a good fib? That's fib 4. So step into should now step into a fib with the argument 2, because we evaluate from left to right. And n is 2. Perfect. And now it should step into a fib 0. Yep. And return. Okay, yeah, so it's still in this line because, let's rewrite this. Because it first evaluates the condition and then evaluates this, and these are two separate statements, so we don't step over these. Step into. Nope. Step into. Oh, I stepped over. I'm a fucking idiot. Stop. Debug. Step into. Nope. Step into. Nope. Step into. Yes. Return. Step into with 0. 1. Well. Then we step into again. Oh, this is so much fucking fun. I cannot believe it. And we're done. Oh my fucking god. This is all worth it. I'm sure there's a gazillion bugs. There's git commit. Added source level, step over and step into. This deserves a smiley face. Oh, I'm so happy. I'm also happy that it just works with the external functions. This one's gonna be and another lurch. Hi. Debug. We step over this, and then we have a lurch. Perfect. And then we wait for 5 seconds. So we can step now. We can try stepping until those 5 seconds are over. Perfect. Fuck, this is cool. Amazing. That's fucking awesome. Oh, I'm really happy. So what's left? When you have the locals, like in this function, then we need to determine what the, thank you, Chronoseller. When we have locals, so we want to display the locals somewhere. I will just create a new div somewhere where I push in the currently active locals. So this whole thing, this low level view of stuff, needs to get replaced with something that lets you select the frame in the call stack. That will then jump to that line in that call stack, and also a panel that shows you the variables within the frame in the call stack that you are, and those variables need to be alive for them to be shown in that panel. And I think I'm gonna do that tomorrow because I'm really tired, but I'm really fucking happy that this worked so well. When did we start? So that was 2.5 hours to have a source level debugger. That's fucking great. This is awesome. I'm very proud of myself at the moment. Sometimes you need those moments. So cool. Step over. It's so fucking cool. Very cool. Okay, guys, I'm gonna call it a day. Thanks for coming by and seeing me happy. And I will probably do the last stream tomorrow, where I tie this all up and create the final version. That's gonna be used on Friday. Well, I hope you had as much fun as I had. Bye.